Hi, my name is Kiran Baburaj. Welcome to Career Campus Pro YouTube channel. What if I told you the technology behind your keyboard's autocomplete feature could be built in just few minutes? Yes, today we are going to visualize the Trie data structure, the brilliant tree-like system that powers lightning-fast word searches. Let's dive into step-by-step visual guide of Trie data structure. Every Trie starts with a root node. Think of it like a trunk of our tree. And notice how our root node is empty. This is intentional. It serves as a starting point for all our words, like the entrance of a maze of characters. Now let's add some words into our trie. First we will insert the word can. First we add C as our child of our root, then A branch off from C, and finally the N that completes the word marked with a dot indicating the word ending. And next we add the word Java that creates a completely new branch. Each character gets its own node because this is our first word with these letters. Next, when we add the third word, that is class, notice how it reuses the existing C node. This is the prefix sharing in action, one of the Trie's most powerful features. It saves the memory by not duplicating common prefixes. Alright, next let's search for the word. First we will search for the word class. Watch how we traverse the tree. We start at the root node, follow C, then L, then A, then S, and finally last S. With the marker that is the end of the word, it is success. But what happens when we search for the car? We can follow C, then A, but not R. This is how our trie quickly tells us when there is a word exists or not. Finally, let's see how we can delete a word from the trie. We will delete the word can. First we identify the path and remove the end marker. Then working backwards, we remove the nodes that aren't shared with other words. And we keep the node C because it is still needed for the word class. Let's break down what makes our trie work. Each node stores a character and tracks if it is word ending or not. Operations like insertion and search run in order of m time where m is the word length. The structure optimizes the space by sharing common prefixes. Let's implement the trie data structure using Python. The trie consists of two main classes, trie node and trie. Think of each node as a character container with branches leading to other characters. These branches form complete words as we traverse down the tree. In the child node class, each node has children dictionary to store its child nodes. The is end of word flag help us to mark whether the word complete end. The trie class is simple, starting with just a root node. This empty root serves as the entry point for all the operations. Now for the insert method, we start at the root node. For each character in the word, we check if it exists in the current node's children. If not, we create a new trie node for that character. We move to the next child node and continue. Finally, we mark the last node as the end of our word. For the searching, we start from the root. We traverse the character by character. If any character isn't found, we immediately return false. If we complete our traversal, we check if it is marked as the word ending. This gives us the exact word matches. But we don't stop there. This starts with the method adds powerful prefix searching. It follows the same traversal pattern but returns true as soon as we complete the prefix. We not need to check for the word endings. Perfect for auto-completion features. And for the deletion, we traverse to the word's end, checks if we have found a valid word to delete, unmarks the word ending, then carefully works backward, removing the nodes only if they have no children. They are not marking the end of any other word. And this recursive logic have to check each level of depth, character by character handling deletion. maintaining the integrity of the stored words, and return true only if the deletion is successful. If you found this video helpful, please don't forget to like and subscribe. Happy coding, thank you.